Okay, shall we get going?
Yeah, good for me.
Okay, then let's get started. So today for SysRead, it's my great pleasure to introduce Zain Ruan from MIT, who is going to present to us on an upcoming OSDI paper about a system called AIFM, which does high performance application integrated farm memory.
Thanks to all for attending this talk, and thanks to Multi for hosting this. And my name is Zain. I'm a PhD student from MIT, and I'm excited to be here to present our OSDI paper, which will be published in this year. And in this work, we built AIFM, a high-performance system that leverages the idle memory of remote servers. And this work was done by me, Multi, and our collaborators, Marcos from VMware and Adam from MIT. Memory-intensive applications are widely used in our daily life. By putting the entire application working set into the main memory, they offer significant performance benefits compared with the traditional disk-based applications. However, meanwhile, memory is also a highly inelastic resource limited by the server physical boundary. Your application can never overcommit memory, otherwise they will be killed by the operating system. Out of memory is very common in real life. For example, many people have encountered this problem when using Python pandas to process large-scale data. One obvious approach is to simply over-provision your memory for peak usage. For example, you can find a super large 2 terabytes memory instance in AWS. However, that's super expensive and people cannot afford it. A trending alternative is to leverage the idle memory of remote servers. And that leads to recent farm memory systems. As you can see in this diagram, the local server can access the farm memory using the network. And thanks to the narrowed performance gap between the network and DRAM, farm memory may offer performance comparable to a local memory. And in farm memory systems, when running out of your local memory, instead of killing your task, OS can swap out some data to the remote farm memory to make room. The idea of farm memory looks promising, but how does it perform on real applications? And here we use a real-world data analytics workload from Kaggle, which is an online data science community. If we run this workload completely using local memory, we will get 100% performance, and that corresponds to this black ideal line. However, if we provision the farm memory systems with 25% of local memory, or in other words, 75% of farm memory, it wastes 70% of performance. This leads to our design goal. How can we reclaim the lost performance through a better system design? And in this work, we designed a new system called AIFM that achieves this goal. But before introducing AIFM, let's first dive into the existing farm memory systems to see why they waste performance. Existing farm memory systems are built based on OS paging, in which OS swaps out pages between local memory and farm memory. However, this design faces two main challenges which leads to low performance. The first one is the performance in the semantic gap, and second one is the high kernel overheads. And next, I will explain these challenges in detail. Applications read-write memory in the object granularity, while in paging systems, OS swaps memory in the page granularity. As you can see in this diagram, one memory page can contain lots of objects, which are represented using these small circles. Even if the application only accesses a single remote object, the OS has to swap in the entire page, which leads to a large amplification. OS also have no application knowledge, which makes it very difficult to make good decisions. For example, if application is traversing a linked list, what OS is just a sequence of random memory accesses. Therefore, it's impossible for OS to do prevention. The second challenge in paging systems is its high kernel overheads. For example, When the application accesses a remote object, it has to use expensive page faults to invoke the OS handler for appropriate processing. And this leads to expensive kernel crossings and convoluted kernel code paths. If the requested page is not prefetched yet, OS has to swap in the page using netbook. To avoid expensive kernel crossings, it has to busy poll the netbook response, which wastes lots of CPU cycles. An interesting thing to note here is the raw netbook latency is only 6 microseconds, but you actually have to spend 15 microseconds in kernel to access the file memory. As a result, existing paging systems achieve low performance, but high transparency, since no application code change is required. Another way to use file memory is using RDMA to manually manage objects. It is able to achieve high performance, but requires significant programming efforts. In this work, we built AIFM, which sacrifices some transparency, but achieves significant performance improvements. Let's take a look at how AIFM achieved this. The key idea of AIFM is to swap memory using a user space runtime instead of OS paging. Therefore, it's possible to achieve significant performance improvements. In realizing this idea, we addressed two challenges I described already. And AIFM solved the semantic gap by using a remotable data structure library and avoids the kernel overheads with a user space runtime. The two additional challenges in the bottom are also critical for achieving high performance. For the third challenge, on the local memory pressure, reclamation happens, which pauses application threads and impact performance. AIFM provides a pauseless evacuator to avoid such pausing. And finally, there is still a performance gap between network and DRAM, and AIFM alleviates this performance gap with a remote pool agent. Next, I'm going to introduce all these key components concretely. First, in AIFM, the application code is running in a user space thread. It uses our library APIs to access our remotable data structures. In the library call, we understand what's application doing with the data structure, and therefore we can record the application semantics. The semantics information can be leveraged by the data structure prefetcher to swap in the future data, so the application thread may never get stalled on making the data structure access. AIFM offers programming primitives for developers to build their own remotable data structure. Do you know how to?
Then there's a question from Sriram, I think.
And I guess you've answered the question as I was asking it. The point is, when you say you've solved it by asking the developer to change their program in some way.
Yeah, that's what we mean by we sacrificing a little bit transparency, but we can achieve significant performance improvements. And later we have an example to show what's the application code looks like. And actually, it only requires a little bit change because the programmer just use our data structure to program to write applications, and it's not something difficult.
So I'm just curious, supposing they didn't change their program at all, would they get some of the benefits? Now, is that something you're going to talk about later on in the talk?
In order to use our system, you need to use our data structure library, and that's all for the changes. And if you don't make that change, you don't benefit.
Got it. Thank you.
Yeah, so AIFM offers programming primitives for developers to build their own remote data structures. And one important primitive here is called remotable pointer, in which the pointed object could be either local or remote, as we show in this figure. And this enables object level swapping, as opposed to the page level swapping in the paging system. When accessing a remote object, the pointer API will call our runtime to swap in the object using a simple function call, as opposed to the expensive page faults in paging systems. Since network has a much higher latency than DRAM, swap-in can incur a long wait time. Instead of busy polling and burn CPU cycles, AIFM runtime performs a very efficient user-level context switching to regrant CPU cycles to another application thread.
I have a question, sorry. How do you, suppose you have a system that is file memory and an OOM killer runs on that process. You would then lose that object one at that point, right? So how does the user space runtime deal with missing like objects if they're on a system where that memory no longer resides?
Yeah, actually, I will talk about later. So we have a primitive called dereference scope.
Okay.
By using that programming primitive, the application programmer can just ping that object in a local memory to ensure the evacuator will never evacuate those objects. And we'll have a concrete code example later to show that.
Perfect. Thank you.
So by leveraging this user-level threading, we can efficiently regrant CPU cycles to another application thread while it's swapping the remote object. And later on, when we context switch back, the AIFM runtime has already swapped in the object, so we don't waste any CPU cycles here. As time goes, we use more and more local memory, and it is close to full now. And our runtime evacuator will detect the memory pressure and starts proactively to avoid stalls.
Zain, a quick question. Maybe we'll talk about this later. How does thread one know to yield back? Does the framework tell thread one? Is there an interrupt? How does that happen?
So in our so they're all user level threads, and in our framework, those threads will cooperatively schedule themselves. So in that case, the user thread one will explicitly call yield. It can be explicitly called by the thread itself, or it can be the case that that thread accesses a remote object. So in either case, it will just yield its CPU core, and our scheduler will switch to another thread. And hopefully that thread already finished swapping the remote object, so it can take advantage of these idle CPU cycles there to execute its own tasks. So it's, in short, it's cooperatively scheduling.
I have another quick question, sorry. You described a process evacuator, but I suppose I'm maybe like jumping down here, but if you have a garbage collector running at the same time and it detects that one of your objects is deeply scheduled or like removed, how does a process evacuator communicate with the garbage collector of the system?
So can you say it again? I didn't hear it clear.
Sorry, my question is, if you're running an application which has a garbage collector running in memory, and you have this process evacuator that is trying to like move pointers to remote and local memory, how do you deal with the case where the garbage collector decides to like evict certain objects in memory while you're trying to like run the process evacuator? Like, how do you deal with those conflicts?
Akshat, yeah. I don't know if you realize your audio is extremely scratchy, at least for me. It's really difficult to understand what you're saying. There's something wrong with the headpiece or something, and also at the speed at which you're going, it's hard to parse it back.
Sorry, let me try writing this out in chat. I need to fix my system. Yeah, let me try writing this out in chat, and hopefully that'll work.
Maybe write it in the text.
But Zain, Akshat's question was, how does the evacuator interact with the potential
garbage collection, right? Yeah. What happens if a GC happens while the evacuator?
Got it. Yeah.
That's really.
I got it. Yeah. So our system is actually based on C++, and in our case, we don't have a garbage collection that's to free the dead object in our program. So in our system, we just rely on reference counting to free the dead object. So essentially, we don't have a garbage collection phase, so we don't need to do tracing and.
I think a more accurate statement is you're assuming that people are not using a garbage collector, right? Because you could be using a conservative garbage collector or something like that. So it's not like you can't say there isn't one. You're just assuming there isn't one.
Yeah, and more importantly, the garbage collector actually aims on freeing the dead object, and our evacuator will never touch those dead objects. They will only touch the code but live object. So it's more like non-overlapping set between them, and they will not work on the same object. So there won't be any data race between them.
So even if there was a garbage collected language, then there would not be a race between the garbage collector and the evacuator, because an object that is dead and can be garbage collected would never be evacuated to remote memory, because there's no point in evacuating it because it's already dead. You can just delete the memory, right?
Yeah. The evacuator is designed to evacuate the live object, but the code object, right? So never evacuate the dead object. So in that case, there's no data race. Does that answer your question? Okay, I think we can just continue. Our runtime evacuator will detect the memory pressure and starts proactively to avoid stalls. It easily identifies code objects using the semantic information maintained by our pointer API. And in this case, the evacuator will evacuate those blue code objects to file memory. And our runtime evacuator has a nice pauseless property, which means we don't have to pause application threads during this process. Therefore, evacuation and the application processing happen simultaneously. Now the evacuation is finished and we get enough free local memory space. Finally, to alleviate the performance impact brought by the network bandwidth gap, we have a remote agent in the file memory side, which is able to execute light operations offloaded by the data structure library. For example, the data structure library can offload the object copy command. And in this case, the remote agent performs copy directly at the file memory side. And compared with the naive approach of first swapping the object to the local memory and then copy locally, our offloading approach greatly reduces the expensive network traffic and improves performance. This concludes the main design elements in our system, AIFM. Let's use a simple example to see how we use AIFM. And here is the original C++ code snippet. It uses 3 data structures: unordered map, array, and list. The first thing we need to do is to change these data structures into the AIFM counterparts. And second, in AIFM, you have to access the remoteable data structure within the dereference scope, marked using this red color. And the scope is used to ensure that access objects will not be moved by the evacuator. And this also answers the previous question about the race condition. Finally, our library supports semantic hints. In this case, the array is large and can pollute our precious local memory easily. And therefore, we can make a hint to disable caching on the array access. And that's all for the code changes. And let's see what happens under the hood. By using the iterator interface to access the list, AIFM captures your access pattern and can accurately prefetch the list data. When accessing the hash table, our runtime will automatically cache the hot objects. And finally, within the hint, the runtime does not cache the large data, array data locally, and therefore it avoids polluting the local memory. Yes, what's the question?
Could you be a little clearer about what you mean by, I'm trying to understand that there's a notion of knowledge here, right? You said by using the iterator pattern, your system knows about, but that's a sort of dynamic knowledge or static knowledge. Are you doing source code analysis? Like, how do you know about it?
Yeah, it's a static knowledge because in this case, the programmer calls our list iterator interface. So our API will know you are traversing a list. So we exactly know what you are doing, and we can just prefetch the data in this list for you.
Okay.
So there's a rem list data structure here, right? In the argument to the foo method.
Yeah. Okay.
And that rem list is an AIFM data structure. So it was written by somebody, we call them data structure engineers, by somebody who knows how to use AIFM and who will have embedded the right invocations of the prefetcher in the list iterator implementation. So the list iterator of the rem list will indicate that it's doing this list traversal and that the system should prefetch the next object.
But that's still a dynamic knowledge, right? Not static, because you won't know till I start doing the iteration that it happened. Like you wouldn't be able to prefetch the first one, for example, presumably, or would you?
It's true. So to be more accurately, I think it's two types of information. The first one is statically. So each time you dereference, you use the iterator interface, then we know you are iterating our list data structure, and this is static knowledge. And second, we have a dynamic knowledge. We know what's your current access index, and we can leverage this information to prefetch beforehand, to prefetch the data after your current access index. So that later on when you access the next
why you're
object,
calling the former thing static. I guess I don't see that as static, or maybe we're using the words in different ways. You're not doing like a source code analysis or something like that.
yeah, I don't mean static analysis. What I mean is this knowledge about accessing this data structure, about this accessing pattern, is determined statically as long as you call our API, right? So that information
But
is
it seems to
already
be, it's programmed in the data structure, right?
Yeah,
Someone
it's
wrote
not
it.
knowledge. It's, yeah, okay. I think we're using words in different ways is all that's going on. Okay. Yeah.
So I think you're both right? Zain is right in that the program contains static information that a list is being iterated upon. However, I think Sriram and Rodrigo, what you're getting at is that in itself does not cause any prefetching, right? The compiler doesn't insert prefetch calls automatically. It inserts prefetch calls because the implementation of the iterator does prefetching.
I think it's more just a terminology matter. The word static typically means something like, a static analysis or static phase as opposed to a dynamic phase. This is not static. This is inside a human's head, which is a different phase entirely. A human knows and chooses to or chooses not to do something with it. That's not static knowledge, it's human knowledge. And I think it's using the term static for that is really confusing.
Although importantly, this is a different human to the human who's writing the application.
That's correct.
This is the human writing the data structure.
Totally fine. Totally fine. Yeah. Thank you.
There's also a question in chat.
Oh, let me see. What's that? Oh, yeah. So people asking whether those data structures are thread safe. And that depends on implementation. And the current implementation is indeed thread safe. So for example, for the prefetching, we actually maintain a per thread access history window. So we can, if you have multiple threads concurrently accessing the data structure, we can do the prefetching for different, for each thread separately. And the good thing about this data structure is it's written by the so-called data structure developers. And you can capture all type of data structure level knowledge just at the API level, and you can pass this API, you can pass this semantic information to a runtime, so runtime can make very intelligent decisions. Whereas in the OS-based solution, the OS have no knowledge about any things like object or data structure, so it cannot perform any intelligent decisions on that. Okay, let's back to the presentation. And that's just a simple code example. And in our implementation, we have implemented 6 different data structures, including array, list, hash table, and so on. The AIFM runtime is built on top of Shenango and NSDI-9 teamwork to leverage its user-level threading runtime and IO stack. Based on that, we implemented a TCP-based file memory backend.
Could you give a one-sentence introduction to what Shenango is for those of us who don't know it?
Yeah, Shenango is our previous work, and we leverage that work for its user-level threading runtime and IO stack.
No, but what is it?
So it's kind of a very fast scheduling system.
Okay. Yeah. Okay, got it. Thank you. That's what I need to.
And in implementation, the core runtime has 6.5K lines of code, and the data structure library has 5.5 lines of code. In addition, we made around 800 lines of code change to Shenango. In our evaluation, we use 1 compute server and 1 file memory server, and both of them equip a 25 gigabits Ethernet NIC. Our evaluation focuses on answering 3 questions. First, how does AIFM perform application with different computing intensities? And second, how does AIFM compare to the ideal case that only uses local memory? And finally, how does AIFM compare to the state-of-the-art paging system, FastSwap?
Zain, a quick question.
Yep.
and it's totally fine to say this is out of scope. Do you allow two clients to share the same remote memory host, or is it just one-to-one?
Yeah, the current implementation does not allow sharing, and I actually think that's a benefit, right? If you take back to look at old related work like distributed shared memory, they allow multiple clients to share the server memory, but that will incur a lot of cache coherency traffic between clients, which significantly decrease the performance. So we made a decision that in our abstraction, we don't allow sharing. And that's the key to achieve high performance, actually. But I think interesting future work is to allow sharing, but at a more cost-grained. So like each time, only one client can do a lease and to access that remote memory, which exclude other threads to access that. Does that answer the question?
I have another question. Why did you choose to use TCP?
Yeah, that's just the implementation choice. The reason is our system is based on Shenango, and we are leveraging its I/O stack. And currently, that system only supports TCP and does not support RDMA. And as long as Shenango supports RDMA, we can seamlessly upgrade to RDMA. Okay. And finally, how does AIFM compare to the state-of-art paging system, FastSwap? To answer these questions, we first use a micro benchmark to evaluate all systems under different computing intensities. The x-axis is the microseconds of a compute per file memory access, and therefore the compute intensity is increasing from left to right. The y-axis shows the performance normalized to the ideal local-only version. The performance of FastSwap, that's a state-of-art paging system, increases when the computing intensity increases. That's because the memory access time becomes less significant when the computation is more intensive. And yeah, there's a question in the chat. Let me see. Oh yeah, so I will actually introduce this later, use a concrete application example. So the main idea is for some computation that have very low compute intensity, instead of performing those computation at your local compute server, you can just ask the compute server to offload the computation directly to the memory server and to perform that computation at the memory server. In this case, you don't move the data, which is expensive. You just perform computation at the remote site, which can efficiently take advantage of the high DRAM bandwidth and avoid the network bottleneck. And later on, we have an example to cover that. And for the FastSwap, it requires about 50 microseconds of a compute per file memory access in order to achieve a near ideal performance. And 50 microseconds is too large to be shown in this figure. However, for our system AIFM, its performance increases much faster and achieves near ideal performance with only around 1.7 microseconds of compute per file memory access. That's because AIFM has a better latency hiding technique and no kernel overhead. The figure can be divided into two regions according to the application compute intensity. For the blue region, our paper offers a synthetic web frontend in which AIFM achieves a 13x end-to-end speedup over FastSwap. And in this talk, we instead focus on the application in the gray region. It's a more challenging case for AIFM since it has a low compute intensity. In this case, we use an NYC taxi analysis workload. And here, DataFrame is a C++ open source data analytical framework, which is similar to Python pandas. It's a real workload from Kaggle, which explores different trip dimensions. The dataset is huge, which leads to a 31 gigabytes full working set size. And to port this application, we modify about 1.4K lines of code out of 24K lines of code, which takes 5% days to complete. An important aspect about this application is that it has a relatively low compute intensity, and therefore our system is unable to hide the file memory latency completely. To address this issue, we keep complex operations local and offload very light operations. For example, copy columns to the remote agent in the file memory side. And AIFM's offloading capability helps us significantly reduce the expensive data transferring over a network. Let's see how does it perform. The x-axis shows the local memory ratio used in the for the working set from 0 to 100. And 0 means only uses file memory, and 100 means only uses local memory. The y-axis shows the performance normalized to the ideal version. First, unsurprisingly, both FastSwap and AIFM achieves ideal performance when using 100% local memory. However, when we decrease the local memory ratio, AIFM's performance decreases much slower than FastSwap. Specifically, AIFM achieves 77% performance with only 3% local memory, and 95% performance with only 23% local memory. Our paper also includes other experiments, as we listed here. So in a synthetic web front-end, AIFM achieves up to 13x end-to-end speed up over FastSwap, and in data structure microbenchmarks, AIFM achieves up to 81x speed up over FastSwap. And finally, in our design drill down section, we also evaluate our key design elements separately, and our results shows none of them is dispensable. And we encourage you to read our paper for details. The first type of the related work is the OS paging system we've discussed, like FastSwap and LIP. The second type of the related work is distributed shared memory. And compared with them, AIFM offers a different memory abstraction without sharing. And AIFM is built on modern data center hardware. Finally, GC is similar to AIFM's memory evacuation. And the main difference is GC aims at freeing the dead objects, while in AIFM, we aim at moving the live but cold objects. To conclude the talk, we present AIFM, application integrated file memory. And the key idea is to swap memory using a user space runtime instead of OS paging. To realize this idea, AIFM has two main components. The first one is its data structure library, in which AIFM captures application semantics. And the second one is its user space runtime, which efficiently manages objects and memory with low overheads. Our evaluation shows AIFM achieves a 13x end-to-end speed up over OS paging systems. And the code is released at GitHub. Thank you for listening, and I'm happy to take any questions.
Thank you, Zain. All right, we have plenty of time for questions, so let's have a great discussion. And as usual, we'll give preference to students. So raise your hand on Zoom or just unmute and speak, but we'll make sure that students get priority.
So while the students are warming up, if I could just throw in I think I spaced out a little bit near the end. Can you just say what your comparison was to Treadmarks again? Because that's the last time I ever thought about these questions, and that's work I know well. So I'm just trying to make sure I understand the relationship.
You're asking for the related work here?
Yeah.
Compared with which one? Sorry. You mean compared for the with the garbage collection?
Distributed shared memory, the Treadmarks paper.
Yeah, so I think our system is different with distributed shared memory in mainly two aspects. So the first one, we offer a different memory abstraction, and we don't allow sharing, and that's the key to achieve good performance. Because sharing will trigger lots of cache coherency traffic using network, and that's very expensive. And the second aspect is we are different in technology. So those distributed shared memory are built in late 90s and use the slow hardware at that time. And many design choices need to be revisited with this modern data center hardware. And our AIFM shows how to build a practical file memory systems using this modern data center hardware.
I'm trying to identify where in your talk that showed up.
Well, in this talk, we don't have like a section specifically compared with the distributed shared memory.
No, I'm sorry. What I meant is I didn't see, I'm trying to page back in where in your talk there was a dependency on modern hardware that's somehow different from the 90s hardware. That last point, that's what I'm trying to figure out.
Yeah, one important aspect is like network has become much faster, and so you can actually achieve good performance with this fast network. But the challenge is how to utilize this fast network, right? And in our work, we have like plenty of techniques. Like we have lots of user level threads, and we can hide the network latency and do active prefetching to utilize the network bandwidth.
Yeah,
as much
yeah,
as
yeah,
we
yeah, yeah.
could.
Okay. Yeah.
Also, slide free,
case,
Shriram.
yeah. So the ideal case is like
Slide 3, you said?
Slide free, there's a fast network that shows up.
yeah.
Okay, got it.
So the ideal case is like our runtime can do the prefetching in the background, and the prefetching speed could be even faster than the CPU accessing speed. So even you are accessing the remote memory, your CPU never gets stalled. So from CPU's point of view, it just looks like accessing the local memory.
Yeah. Okay. Yeah. Good. Great. Thank you.
Thank you.
So there are a couple of questions in chat, which I will read out so that we get them in the recording as well. Akshat asked, you use C++, which supports custom allocators, which make a user space runtime easy to develop. What about applications written in languages which don't expose custom allocators? So for example, JavaScript.
So the question is about the case that don't have custom allocators. Well, in that case, I would imagine you can still offer a kind of a library function, kind of wrap this functionality in your library function, like providing this allocation call. And even you don't have this native support in your language, you can still have a separate library functions. And you can just call that library functions to do memory allocation and deallocation. And that's important for our system because we have a different abstraction for pointer. It's called remotable pointer. So you must use like our function call to allocate this remotable pointer instead of the native pointer. And I think it could be done in other language through a separate library extension.
And the second question is also from Akshat, is there a way to support this for such languages, for example, through foreign function interfaces?
Yeah, I think that's what I mean by the library extension. Yeah.
Of course, you could also integrate with the runtime, right? So you could modify the JavaScript runtime or the JVM to support these interfaces.
That sounds like more intrusive, and I don't know whether people will take that because it requires to modify the managed runtime, which looks unsafe, I think.
I have a question.
Yep.
I might have missed this, and if I did, apologies, but I'm wondering how you controlled the local memory ratio in that last experiment you described.
Oh, I see. Yeah. Let's look back. So there are two systems showing here. One is FastSwap, and that's an OS-based approach. You can adjust the local memory ratio using the OS C group setting. So basically, OS provide a functionality to throttle the memory usage for application, and that's for FastSwap. And for AIFM, it's even easier. So at the initial, so AIFM is a library-based approach, and at the initialization stage, you need to have a library call to initialize our runtime, and that library call accept an argument that is the local memory size you want to use for this execution. And in that argument, we just pass these parameters there. So later on during its execution, it will just use at most that local memory amount.
Great, thanks.
How much resources does AIFM require on the local host to manage the memory?
Yeah, so you don't need additional you do actually, yeah, I think. So in order to use our local memory, so basically there are two main components. One is this library extension. So each time when you access our remotable, so-called remotable pointer, we have a read-write barrier in this pointer API. So each time we access that pointer, dereference that pointer, it will trigger our corresponding runtime code. But that's just happens in the library implementation. It does not require any additional CPU resource there. But there are second components, is our runtime, and it does evacuation when your local memory is mostly out of free memory space. And in that case, you need additional CPU power to execute our evacuator, try to move your object to the remote memory. And you need additional resource there.
Yes, so do you have numbers on how much additional resources you needed for your benchmarks?
Yeah, we do actually include those numbers in our paper, but it's not in the presentation. But in general, it's very small. So usually it's just like about 10% of your overall CPU capacity. And I think people are willing to make this trade-off because by having this, by sacrificing this small amount of CPU power, you can actually increase a lot of your local RAM capacity by leveraging the remote RAM, right? And that can significantly cut down your total cost of ownership.
So piggybacking on that, what is the remote cost, right? Because you have to have this other thread doing operations there too.
Yeah, currently there are two types of cost. So the first type is because we are using a TCP-based backend, so the remote CPU also need to get involved in processing the network packets. But I would argue that parts of the overheads it could be removed in the future, as long as we migrate from TCP into RDMA. So in that case, we can just bypass the remote CPU core. So that's one aspect. And second aspect is, in our system, we have a component called remote agent.
Yeah.
So that agent, we can actually offload computation to that agent. So that requires additional CPU power. But the point is, we will only offload the computation that has very low compute capacity, very low compute intensity, like, for example, like just pure memory copy, or just a simple aggregation over a range of memory. And that will consume very little of CPU resource. And in our evaluation, it just requires about like 1 to 2 cores to process the request.
So one thing to point out there also is that if you're already signed up for farm memory, right? If you already want to use farm memory because you need the capacity, then the alternative to having this remote agent do the work on the remote side is to copy the data over to the local side, do the work and then copy it back, which will use more CPU cycles, both in aggregate and also on the remote side, because you also need to use CPU cycles to copy the data, right? So the trade-off here is to say, well, rather than copying the memory once to the local side, then copy it locally and then copy it back, which is free copies, we just do one copy on the remote side, which is the same what the remote side would have done anyway, because it would have had to copy it to the network anyway. In fact, it even would have to copy it back. So it's actually half of the work that it would do on the remote side otherwise. And we still reduce the computation in aggregate by moving it to the data.
By the way, Marty, I think the original copy cost would actually disappear if you use RDMA, because
that's true. If you used RDMA, these are a little bit different, though you still have to send the data across the network. So you're still burdening the network in that case.
Yeah, correct. I think the main point here is, as long as you are willing to use a little bit CPU power at the remote side, you can significantly increase your performance because we avoid the network bottleneck by eliminating the expensive data movement between your local CPU server and the memory server. Yeah, what's your question?
I guess I would have liked a little more discussion during the talk, and maybe hopefully it's in the paper about what happens when you mutate the remote data.
Yeah, the only way to mutate the remote data is to first swap in that data to your local.
It's single writer.
Sorry?
Nobody else is touching that data. Sure.
Okay. I see. Well, no, but so that's two issues, right? So one issue obviously is like the contention for the data and like the sort of multi-threading aspect of it, and so that's what you've answered. But the other part is also being able, the cost of like moving mutations across, right? There was a lot of work that was done back in the like the Corba and Obj and all these other systems of trying to deal with the fact that you have these remote mutable data. The sort of the follow-on to initial RPC work was you have these remote mutable data. How do you efficiently translate mutations back without having to copy the whole thing, et cetera, right? So there's lots of architectural choices about what happens when you fetch a remote value, mutate it locally, now what?
So in our system, as long as the data is fetched into your local CPU server, then it can be mutated even with multiple threads. And in that case, the data will marked as dirty in our pointer API. So later on, when the evacuator try to evacuate that object, it knows this is dirty, so you must write back. So the data, so the updates will be written back to the remote side to ensure
right. But if you might have a large object, you might have mutated only a small part of it.
That's true. And yeah, that's totally correct.
That's the part I'm getting at, right? Is like even so one part I needed to hear was that there's only one writer, and you're saying it could be multi-threaded, but that's still one sort of from a global perspective, that's one machine. So that's very clear now. But you still have lots of choices. And when it comes, because you're talking about network performance as well and so on, it really does matter like how much data you shift at each point.
Yeah, that's a very good suggestion. If you only have a partial modification of your object, what you really need to write back is just that portion of updates. And I think in this aspect, our system has a big advantage compared with the OS paging system. Because in OS paging system, you have no choice. You can just write back the whole page. But in our system, you can actually have a more lightweight object definition by using a more fine-grained object. Then in that case, you can significantly reduce the amplification because you only need to write the partial of the modified data back.
Well, I mean, the other way of looking at it is, you are asking people to use your APIs anyway, right? So your APIs have more control over what's going on. And so presumably you can track which part got updated, whereas the OS is just like the page is it's the unit of abstraction. So
yeah, that's a good suggestion. So it's kind of each time when you dereference an object, you will just tell the range that you are going to operate on, and that information could be tracked by the runtime efficiently. So each time when you write back, you only write back that range. Yeah, that's a good suggestion. Thanks.
But I think the baseline is that AIFM encourages you to decompose your objects into more fine-grained objects so that you get less amplification. If you have a giant image of 12 megabytes and that's your object and you modify 1 byte in it, you're not going to get a big advantage over paging systems, right? Because that's many pages anyway, there wouldn't have been much amplification. But if you have something like a list or a hash table, you win big time because it's much more fine-grained there.
Correct. But I also think this range API is quite useful because in some cases, the programmer just don't want to make significant efforts to like decompose your object because that will require lots of application code changes. And if you can just indicate the range, you only make changes on the object referencing code, and that just incur less code changes.
Well, and you've also already taken the first step, right? There's like there's the valiant effort, which is you don't change anything about your code, and I will do like heroic amounts of work to make everything work. But you've already done that first step, which is say, I'm going to change the APIs you have to program against. And once you've done that, like you're halfway there, right? Now you can exploit that fact and maybe, or even incrementally, right? Ask for slightly more changes. If they change that code more, they get more incremental performance, things like that, right? It's you're off to the races at that point. So.
Yeah,
I'm saying I like this. So
yeah. One very good aspect about our system is we can bridge the semantic gaps between the application and runtime by capturing lots of rich application semantics. And I think the previous, your suggestion is just one example. And another example I didn't show in this presentation is if the application is accessing a data structure and the application and the programmer knows exactly about its accessing pattern, then you can just disable our built-in runtime prefetcher, and instead passing this accessing pattern directly using our API calls. So our runtime will do perfect prefetching in that case. I think that's just another example about this benefits of having this rich semantics.
Yeah, I think I have a question that's kind of related to that, which is, so you, again, going back to this experiment that you had here, where you say you're offloading cheap work to far memory to the remote. So how do you determine what the cheap work is?
Yeah,
like,
so currently
determine workloads that qualify as cheap work.
Yeah. So currently, I would say it's done manually, right? It asks people to identify those very light operations. And specifically for this example, we actually offload two types of operation. Let me see if still the slides is there. Yeah, I think it's there. Yeah. So in this workload, we actually offload two type of light operation. One is just pure memory, moves like copy or shuffle or columns. And second one is just a simple computation like aggregate column. And they are easy to identify by the programmer. And that's the current method. It just requires manual effort. And I think a very interesting future work is to develop a compiler. Say you feed the original code to this compiler, and compiler will automatically identify those light operations and generate the corresponding remote code, and all the process will be automated. I think that's an interesting future work to explore.
I mean, this isn't necessarily cheap, right? Like your column could be massive. And if you're doing a tight loop, like what, so how do you determine this type of workload?
Yeah, what I mean by cheap is its compute intensity, or more formally, it's defined by the kind of number of computation per byte. So in that case, if you are just move, then it's very cheap.
It's per. Okay.
Yeah,
gotcha.
Correct. So you can just think about the naive case, right? The naive case is you don't offload. You just read that data back to your local memory. And in that case, you already need to copy all of your data. And now in our case, we just said, well, you just pay additional costs. You just add a single move instruction in your loop body. Then you just do that copy at the remote side. So compared with the naive approach, you are only paying a little bit more CPU power there, just adding one instruction in the loop body. Yeah.
Right. So long as the operation is cheaper than a copy for every byte.
Yep, correct.
Then that's okay. So that might be a good qualifier.
Yep. So and ideally that actually could be automated, as I said. You can combine the both static analysis information or even some dynamically profiling runtime information to decide which part to offload. So you don't need to manual effort. You can just let compiler to automate this process.
Okay, so we have 3 minutes left now, which I think gives us time for one or at most two more questions. Thanks everybody for the fantastic question. Last call at this point. So if you haven't asked a question yet, this is your opportunity. And if you have already asked a question and nobody else wants to ask one, you get another one.
Yeah, I have a question. So this is really cool, but like you have to choose which data structures to implement, and also on the remote side, you have to choose which operations you are going to implement in the agent, right? So how did you choose, and when are you going to consider yourself done? Like how do you, right?
Yeah, I think in our scenario, there are three different roles. The first one is our system, this core library, and that's provided by us, right? And second type of role is the so-called data structure developers. And they understand our system and can build a bunch of data structure libraries. And that's just a one-time effort. So after they build in this data structure library, there are another type of people called application programmer. They can just use those library and they don't need to understand our system at all. And they just use this library function to write their application, and it's pretty easy. And you can just imagine, like for C++, we have STL library. And that's just built up by a bunch of expert, just one-time effort. And later on, every people can use that to write application without understanding anything about your system.
Okay. It is almost 1 p.m. So I think what remains is to say thank you, Zain, for giving this presentation. Very enjoyable. And thank you all for coming. Next week, there is no sysread because it's OSDI, and a bunch of us are going to be attending OSDI. The week after, we have Irina Calciu from VMware, and I will send out the talk announcement soon for that talk. So I will see you back here in 2 weeks. Have a good weekend.
Is there a reference for the paper somewhere? I missed that one.
On my website.
All right.
Or on Zain's, I guess. Yeah, we can get you a link.
All right. Thank you. Thank you, Zain. That was great.
Thank you for attending the talk. Thanks, everyone. Thanks, Marty, for hosting this.
Thank you. No problem. My pleasure. See you soon. Have a good weekend.
Bye. Have a weekend.